Well, hello, my name is Bruce Naj, and here I am at China Lake in California, and I'm here to present to you a very interesting approach to developing artificial intelligence. And the series is called Levels of Rigor for AI Development. And what does that mean? Well, that really means it's about how to control the process of developing AI. So that process includes requirements, it includes architecture, it includes algorithm design, algorithm code, and finally tests and evaluation. And so why is this important for you to watch? It's important for you to watch if you want to make sure that your artificial intelligence development is a quality level of development and it meets expectations when you're done. And how are we going to do that in this series is we're going to basically say, how do you control as much of that process as possible in order to produce a quality product in the end. In this first video, we're going to focus on AI, and we're going to explain it, I think, in a very unique way. And I think you'll enjoy it. And then after we explain AI, what we're going to do is we're going to actually introduce you these control areas, these tasks, these levels of rigor, and just a brief explanation, a brief description on why they're important and how they'll make such a big difference in how you're developing AI. So with that said, let's jump right in. Well, I'd like to introduce you to my helper. I brought him in to assist because there was just something about the way he looked. Together, we're going to introduce and describe the topics of artificial intelligence and level of rigor. Here are some questions we'll answer. Here's terms that we'll use, and we'll also describe some new terms that will be introduced during the video. So here are the questions, and they're very basic. What is AI? Why is it popular? What's the difference between an algorithm and a model? And you can see that we're going to talk about autonomy, semi-autonomy, and then finally get into level of rigor. Then we'll go into some terms. In this video, we'll talk about mathematical techniques, samples, and instances. Finally, we will get into more of the meat of artificial intelligence. We're going to introduce what models are as compared to algorithms. We'll start to talk about training material and data sets that are used by AI algorithms. And then obviously we're going to finish up with a very healthy discussion on level of rigor tasking. What's the big question? How is this AI series different from the others you've been watching? Other series focus on terminology and mechanics, and we'll do that too. Yet what we're going to focus on is level of rigor tasks. That's focused on ensuring confidence that the AI being developed will meet expectations. So we're going to discuss questions and considerations that will give you the power and confidence to ensure your success. And those questions and considerations will be discussed in detail in the form of what a system looks like. We're going to talk about a system in terms of requirements, architecture, design, code, test, and evaluation. What AI is, what is it, right? Well, we consider it to be a function that mimics levels of human intelligence. And because of that, it can free humans from doing risky and pretty manual chores. And it does it through algorithms and mathematics. But because of that, it takes a real special approach to train it and allow it to do these things and mimic human intelligence. And that's where the challenge is, and that's the reason why we've developed a series on AI level of rigor tasks. Why do we say AI is unique? First, understand that it has a way to learn that is very similar to the way humans learn. And how it learns is based upon samples, and we call them subsets of data. And it learns from that. And from that subset, it's able to learn a larger set of data outside that subset. And this process of learning from a subset or example mimics the ability to be taught something very specific, like what is a glass of water, and then recognize it in other similar forms without additional training. This is really the marvel of how humans learn and it's passed on to AI systems, and that process is called generalization. And it's a wonderful thing to see a set of math and algorithms be able to do it, but unfortunately it's also a bit dangerous. So when we say what is AI, understand that it's very unique, it's very marvelous, but it's also very dangerous, and we'll explain why. What AI is not? Well, it's not Terminator, it's not any of the things you see in the movies, it's not a superior sentient being, it's not all-powerful with unlimited capability. It can only do what you train it to do, and honestly, you can't even train it to do some of those things you see in the movie. Not yet. It has no instincts, insights, intuition. It has none of that. There's no emotional intelligence. I will say that it's not even developed like traditional code. That's what makes it challenging. It takes a lot of data to train it to do a very simple task, and that's what makes it very challenging as well. So if AI is dangerous and it's also marvelous, maybe that's why we have to answer the question, why is AI now so popular? So let's give a little background. First, artificial intelligence has been able to evolve because our processing power, our computers, our increased storage, it's just gotten better and better and better. So we can take those large amounts of data and process it more readily. So therefore, remember when I said that AI needs large amounts of data? Well, we're sort of set up to do that now. And you see various examples of banking, search engines, driverless cars. So wonderful things are happening because of this computer boom. Yet, always remember that it is based on mathematics. And in AI, sometimes it's mathematical intuition, sometimes even art, in order to make AI work properly. So we created these great AI frameworks, we created these great things that can develop AI, and it gives us this vast possibility of what ifs, and that's the marvel. AI has become popular because we now have the technology with the computer processing capability, the frameworks to develop it very easily, and it allows us to look at what ifs and maybe possibly emergent solutions that can finally become more like the science fiction movies that you've seen. Now that we've finished the basics, let's get into the elements of an AI algorithm. So the first element that we're going to define is called an input format. The input format is based upon the data you collect. It represents human knowledge, maybe possibly measurements. The second element would be requirements. What is required of the algorithm to mimic? Does it require it to analyze something in order to recognize something? Does it require it to measure something to come up with some type of number solution? The third element that needs to be focused on is that once we understand the input format, what it's required to do, we now have to look at what are the mathematical techniques that are going to be used. And this is where some of the art in terms of how you design the algorithm needs to be performed. So in terms of mathematical techniques, we look at what assessment is, how we're going to categorize something. If it's dealing with numerical solutions, we're looking at approximations, or term regression, where it's another form of approximation in the way we look at a number. The final element would be an output format. We know what's going to go in, we know the input format, we know what the requirements are for what we need to mimic, we have the mathematical techniques that we're going to use. Now, when it finally makes its decision, it identifies a label, comes up with a number, and when it's represented properly from the input to the output, you're seeing an expression of knowledge, right? Here, I give you this fruit. That's the input. Oh, it looks like a piece of fruit. And the output is, that is an apple. Those are the elements of an algorithm. And if you remember that, you've just started your journey to have more control over the process of developing an AI model. Now that we understand the four elements, let's see how those four elements are used to make an AI model from an algorithm. We start with an algorithm and we add math techniques and functional requirements. Those are elements 2 and 3. From those math techniques and functional requirements, we begin the training process. Remember, the training process involved elements 1 and 4, the input and the output format. That input format comes from the learning process itself using training material called data sets. And just to make sure there's no confusion, a data set or training data sets are all synonyms for that material in that particular format used by that algorithm to train. And when we do the training, we require a lot of that material, large degrees, sometimes thousands to 100,000s of samples to train the algorithm sufficiently to meet the functional requirements. But what it actually does is it programs the mathematical structures properly in order to perform adequately. The result of that is the AI model. From an AI algorithm to an AI model mimicking intelligence from an input format, element 1, element 2, using the functional requirements, element 3, the mathematical techniques to create the output desired. And the output desired is now the 4th element, being the output format. And that output format is either a label, a text, a number, a group of numbers. And these are examples of expressing intelligence. Quick review: algorithm gets trained and it becomes a model. Algorithm consists of math techniques, it consists of requirements. You have to conform to an input format and it has to conform to an output format. And in that entire process, you've now represented or mimicked intelligence. So at this point, we have an understanding of how to develop an AI model, and I want to thank my helper. Let's make sure, though, that he doesn't get any bigger head than he already has. So I think let's see what some questions are about the material we currently reviewed. And we're fortunate to have Admiral Dillon, who is the commanding officer of this China Lake facility here. And so please, Admiral, what is your question?
Well, thank you, Bruce. And before I even ask my question, I want to just say a few words about how excited I am for the opportunity, led by Bruce, to do cutting-edge work in the field of AI here at the Naval Air Warfare Center Weapons Division. If you look hard at any of the national military strategy documents or the derivative Navy strategy documents, you get a strong sense of how important AI is to the developmental work that's happening across the entire naval aviation enterprise and across the entire Navy enterprise. But figuring out exactly how to apply AI, when you can get the most value out of AI, when it might not necessarily be worth trying to incorporate into a new system, is something that's much more difficult to accomplish. And so it's particularly valuable to the entire organization if we have a set of rules, a set of guidelines, some sort of formal guidance that helps us decide when AI is appropriate to the problem that we're trying to solve. And I think that is one of the things that Bruce's work is allowing us to develop in a more formal fashion. So Bruce, if I could ask you a question, particularly about those guidelines, I was wondering if you could talk a little bit about the importance of having guidelines and the role that those guidelines play in developing AI for operational use.
So, Admiral, you hit it right on the head. No reference to my little helper. And I think that the reason why that question is so important is because guidelines really are making a statement about how to develop a quality system. And we talked about how to develop that quality system, or we will be talking about how to develop that quality system in terms of control and levels of rigor tasking that creates that control. So it's a really important question. It's the reason why we're doing this. In order to literally meet expectations, what are the control mechanisms you have along the way to ensure those expectations are going to be met? And those control expectations, those control processes and tasks, level of rigor tasks, are the guidelines that are needed.
That's fantastic. Thanks for that, Bruce. I, for one, am truly excited about the opportunity that this technology offers to provide advantages to our deployed forces as a result of this sort of careful, methodical thinking and development. And so you're doing very important work, and the entire team is, and I thank you for that.
And thank you, Admiral, because you created a great segue for the next section, talking about operational deployment and what do we need in order to make sure that we operationally deploy it? What does that look like? What does the system look like? And so that creates a nice introduction. And so let's get back into the wonderful world of artificial intelligence. So Admiral Dillon segued us into a great conversation. How do you get AI ready for deployment? Here's my one answer. You make sure that it can meet expectations. But how do you do that? From a data science standpoint, I'm going to describe what they need to go through in order for that to happen. But I want you to keep in mind those 4 elements and where they're going to come from. I won't discuss those specifically. I'll let you do that. But I will discuss it in the form of what a data scientist is going to go through. So a data scientist is told, hey, you need to mimic this type of behavior, AI behavior. You need to do something. Okay, well, I'm going to first take a look at the mathematical techniques I'm going to use, and I'm going to define my software, hardware that's going to be installed, and that's going to be my algorithm. Then I'm going to ask for training material. That's when it gets tough. Up until then, it was nice and smooth. But you see, the training material is in 2 parts. It has to be the input, and it has to be the output. Why 2 parts? The input is what it has to be trained on, but you can only manage the mathematics within the algorithm based upon truth. That's how it updates itself. It says, I'm going to take in these samples, and I'm going to constantly tell you if you get the sample right. And I want you to adjust all your mathematics to make sure that you get that sample right. And so that goes on and on and on, and that's why it takes so many samples to do. The next part of the problem is, what if you don't have enough samples from the real world? Then you have to go to synthetically doing it, and that's where it could cause errors. So the data scientist is constantly worried about if he has enough data in order to properly train the model. What does that mean to you? Your challenge. If you want to have confidence in your AI model, then you better have confidence in how it's being trained. Does it have the right truth? Is it enough? And if it is, right, then you finally get an AI model that you believe will be able to meet expectations. But the model is just a function that's going to fit somewhere in a system. And that function can have a variety of different purpose. And that function is still mimicking intelligence if it's trained properly and has the right success rate. And how you recognize that it mimics properly is in the label that it produces or in the number that it produces. And obviously these are examples of how it's representing, estimating actual truth. But do you have confidence that it can generalize well enough to be successful? And when you're sure that it can meet expectations, that's when you know that AI is ready for deployment. Now that we understand how to get an AI ready for deployment, let me explain why that was so important that we emphasize that. Because when it is deployed, it's going to experience the real world. And wow, remember we said that previously the challenge was getting enough real world data. And also remember that we also said that everything is samples. And we're hoping that it can generalize, remember that term? It can generalize enough so the model can generalize and get the right output. So what happens is you have the model, it's replicating or supplementing a human in some way, but it's part of a system. And what I want to emphasize here is that it is part of a system. That data, that real world, could be being interpreted by other factors within the system, and they would be provided to the AI function to perform, and that output could go into other parts of the system, and together that whole structure would make up the entire purpose of the system. So AI is part of that purpose, and it's either supplementing or replacing a human being. So that in order for it to be effective, that output therefore has to be accurate. it has to be as accurate as possible. It has to estimate truth. And so hopefully, again, in the previous diagram, we talked about how challenging it is to make sure that the truth is being accurately estimated. So you don't want to release that AI until we have a high success rate. And so the output has this high success rate. It's going to interpret the real world. It's going to affect the other parts of the system. And together, that's the way it's going to actually express knowledge. But the key there is to make sure that it was trained properly so the trained output, no matter what type of real world input it's given, can give an accurate estimate of truth of what the rest of the system needs to do. Now that I introduced AI within a system, let's talk about the various ways you can put AI within a system. So obviously you can put AI in a system where the human is not in the loop at all. Or you can put AI in a system where the AI and the human are in the loop together, and the human might be checking everything that the AI produces and then passing it along. Or you can put AI out of the loop or not in the loop completely, and the human is just literally just getting recommendations. That could be a recommendation engine. That could be something that says, hey, do this, do that. Okay, I'll go do it, and the person tells the rest of the system what to do. The final one is that you can put human on a loop. It's very popular. In other words, it's monitoring. It's looking at what the AI is doing, and it will only interfere if it thinks that the AI is doing something that is not appropriate. Let's look at the various types of autonomy. I'm sure you've heard the term autonomous and semi-autonomous. And how I'm going to explain these to you is using examples. One example is going to be a route planner. The other example is going to be a robotic vehicle. And I want you to look at the 4 selections. And as you look at the 4 selections, the first 3 involve autonomy and semi-autonomous structures. Can you recognize which one is autonomous out of the 3? If you guessed the second one from the top, you'd be absolutely right. What about the one on the bottom? Well, the one on the bottom really doesn't have AI participating directly in the system. And therefore, it would neither be autonomous or semi-autonomous. So with these examples, what type of autonomy would you choose for an AI route planner? Would it be autonomous, semi-autonomous? How about for a robotic vehicle? Would you want that to be fully on its own without any intervention from a human? Would you want the human to be in the loop, on the loop? What would you choose? We'll show you what our answers are, and from these solutions, from these examples, actually develop the 14 level of rigor tasks. So now that we just finished reviewing types of autonomy, I think it's a great time to see if there are any questions, and fortunately, we have Mr. Harlan Koima, who is an SES for the China Lake facility. So Harlan, what is your question?
So Bruce, this whole AI thing really brings up a lot of questions. One of the big questions I have is AI really ready to operate autonomously without humans in the loop? That's a big question that we're going to have to answer. What do you think?
So it's not ready, and we're doing things to help make it more ready, but we're going to explain all that during this series on why it's not ready and what you can do to make it more ready. So at this time, when it comes to critical functions, that means that there are lives that could be lost, property that could be damaged. It's certainly not ready.
So then, if it's not ready, how are we going to really be able to implement this in a way so that the operator learns the limitations and how to use it, and also so that we start to inform ourselves in the work we're doing that it will be ready in the future?
So that comes to the question of trust, right? How are we going to be able to trust the system to act autonomously? And that's the whole point of what we're doing. I mean, this is the first series that actually focused on a quality controlled process along the way. And as we refine this process, as people start to use this process, you'll find that we're going to have more trust in how systems behave in an autonomous way. So this is the solution, and I'm not saying that it is a complete solution, but it moves us much more closer to having a completely autonomous system.
Oh, very good, Bruce. And I appreciate the attention that's being paid to these critical questions, because the operator, the warfighter, who will be in combat, needs to have confidence in the systems that they're using. They need to be able to use them, train with them, and build that experience and understanding and trust that's going to be so critical. So I appreciate that you're taking that into account as we're designing and developing. The other thing, Bruce, I just appreciate the effort that has gone into this. This has not been a overnight success. This is something that is years in the making. A lot of effort's been put into it, a lot of dedication, and it's really for one reason. We know the world is not safer today than what it was yesterday or last year or the year before. And we need these advanced systems so that we can move the United States capability forward into this new generation of capability and technology, so the warfighter has the decisive hand, makes critical decisions that will change the outcome of the battle, and that ultimately will be successful to meet the mission that they have gone out to do. So thank you for the work that you're doing and the dedication and your personal dedication to the warfighter.
Harlan, again, thank you, and thank you for the question, because again, I think it leads to the next section where we're now getting in more detail about exactly what it takes to make sure we have a quality controlled process. And to do that, we have a use case that involves several types of AI systems and several types of autonomous systems. So let's talk about that. I just made a statement that we're not ready for a fully autonomous system. And there's a reason why I mentioned that. And it's not because I have that as an opinion. It's because we developed a sandbox that proved my point. And within that sandbox, we developed two specific types of technology that ran a variety of AI functions. One type of that technology was a route planner that we talked about earlier. And we developed it with a human on the loop. Another part of that technology was a set of robot vehicles, and that we developed that with a human on the loop. Those two systems, we actually created a use case. And the use case was basically delivering packages over some challenging routes. So for our robot system, if you notice, we have non-AI functions and we have AI functions. Some of the AI functions we have is a convolutional neural net called CNN, a deep neural net, DNN. Managers of those technologies. We have regular functions, functions that are feeding those AI systems. Does that sound familiar? So we have all of this within our robot system that we are using to analyze to develop the level of rigor tasks. Now the other autonomous system is the route planner system. The route planner system obviously had the hardware aspects to analyze, and the route planner also had software functions. And if you look down the list, on the first column, you'll see naive Bayes for classification, random forest, minimax algorithm. So along with the other non-AI functions, it created a system. And this system supported a variety of inputs. And you see on the right, it had a series of databases. And databases are very important because those databases help to feed the AI model. So you have functions grabbing that data, feeding the AI, and coming up with a result. And when you look at this, I want you to think about those 4 AI elements of an algorithm and see if you could see where they are in this diagram. The route planner system joins the robot system, and together it gives us a good foundation with artificial intelligence functions and non-artificial intelligence functions for us to review autonomy and for us to understand what it takes to have greater confidence in an autonomous system. So let's look at how these two autonomous systems are going to work together. And you might even consider this to be a system of systems. So first, the mission planner is going to determine, with the oversight of a human, what robots are going to be used, what trucks will be used, because the trucks are going to pick up the robots and deliver them to a location. So it's going to figure all that stuff out, what routes the robots are going to follow. Once the planner makes these decisions, the robots will be delivered to a certain location. At that location, they'll be dropped off. They need to avoid certain obstacles along the way as they are dropped off. They're constantly being monitored to make sure that they can handle various hazards along the way and what they're doing. And they also need to make sure that they really don't do three things that are very important. One, they deliver the packages to the people intended. They don't cause any destruction of property, and they obviously don't destroy themselves. And that might take going around buildings, that might take going up surfaces, doing different things, till they get their final location, and hopefully recognize the person they need to deliver packages to, and then deliver those packages intact. So what is the point? Why did we go through all this? Why did we do a sandbox? Why did we go in such detail of developing these two systems? And it was for the point of understanding our autonomy enough to know whether it can meet expectations or not, and why it could or could not meet expectations, and then develop a level of rigor to ensure that when you use what we're asking you to use, that you will have confidence in its development. Because when we applied this level of rigor within this sandbox, we had significant improvements in every one of these systems that we're talking about. Well, now that we just looked at the use case and the details and the challenges that we set up for our AI systems to deal with, I think it's a good time to again go to the audience and ask questions. And I see that Ken Cherkis, who is the department head of systems engineering, is here. Specifically, he has robust knowledge over system safety. So let's see what question he has. Ken?
So Bruce, I have a question with respect to the safety of AI ML developed systems. How are we going to know, what is the point that we will realize that these systems are safe for deployment?
So if I would have any type of level of confidence in anything, I'd want to make sure that it was built with quality. And I know I keep on coming back to quality, and then I'm going to come back to control, and then I'm going to come back to rigor, and then I'm going to talk about level of rigor. And it just makes sense, right? And that level of rigor following what is needed for requirements, what is needed for architecture, what is needed for algorithm design, algorithm code, and finally test and evaluation. So if we want to improve our confidence in a system, we need to ensure that we have control or rigor in the process that created the system.
That's terrific. If you don't mind, autonomous software certainly gets a lot of attention. Software that's completely or totally autonomous gets a lot of safety consideration nowadays, and with respect to artificial intelligence, even more so with the level of rigor. So if we're dealing with your level of rigor assessment, we want to certainly ensure that software is being developed with those lore tips and configuration development, software development ideas and thoughts.
Yes, absolutely. And I want to reinforce to the audience the fact that trust is a very common question. And it's important that the approach we're using, again, the level of rigor approach, the tasking that we're suggesting for you to use, helps improve that trust. And we're going to go into detail associated with 14 level of rigor tasks that will demonstrate why you will definitely have greater level of confidence and trust in the system you are developing. Now it's time to actually talk about the level of rigor tasks. All these tasks were derived from those two autonomous systems we just previously talked about. As Ken mentioned, there's a real challenge with ensuring that AI and autonomy can be trusted to perform as expected. And that challenge comes from having confidence in the development of the artificial intelligence within a system. That's why this video is focused, this whole series is focused on understanding AI development within a system. So let's get into the 14 levels of rigor that were derived from working within the sandbox environment. We're going to get into each one. Our first level of rigor task is called AI function type definition. It specifically defines how to recognize an AI function. That's important because a data scientist might say, I'm developing this function and I call it Mabel. Well, is Mabel an AI type function that needs a special level of rigor, or does it just need to follow typical software development processes? This level of rigor test will objectively tell you how to distinguish between one and the other. The second AI level of rigor task is called justifying AI function needed. And it's specifically saying, do you really need that AI function to perform within the system, or can traditional software be used just as well? And why is it a better fit than traditional code? And it's important to justify why we're taking the added risk. And the point is to be able to describe that and ensure that we're not adding risk when we don't need to. The third AI level of rigor task is called justifying AI functions level of autonomy. It's specifically wanting the data scientist or the program to justify why that level of autonomy is being used. Why is it going to be fully autonomous or semi-autonomous? Or does it need to be autonomous at all? Because the more autonomy it has, the more risk it has. And the goal here is to always reduce the risk of the AI function, because the AI function has both that magical side, but it also has that dangerous side. The fourth AI level of rigor task is called best practice discussion about AI ML development. When we refer to best practices, we're talking about modality of the training data, we're talking about sparse and missing data. These things we'll discuss in greater detail, but they should be part of your considerations when developing a requirement stock to ensure that best practices are being applied both in the program development process and in the data science development approach. And we'll talk about this in later videos. The fifth AI level of rigor task is called Training Set Alignment Test, or TSAT. We developed it here at WD. It defines how well a data sample represents the real world when the model is finally deployed. It actually shows an alignment, and it's a metric, a measurement approach to ensure that you have a quality sample going into the algorithm for training. The sixth AI level of rigor task is called Sources to Attribute Ratios for 1, 2, and 3 nth order matrix, or star N. We also developed this at WD, and we developed it in combination with the previous lore, TSAT. But consider that in TSAT, we focused on the quality of each sample. Now we're focusing on whether there's the right quantity of those quality samples to adequately train the algorithm to become a quality model. And this is unique to WD. We knew that we needed to focus on somehow being able to ensure that our data set is a quality data set and has the right quantity. So just from a common sense standpoint, when combining the quality and quantity of the data set, we can ensure that the model is being developed properly to meet expectations. The seventh AI level of rigor task is called Best Practice Discussions on Data Set Generation. In the previous two lore tasks, they were WD focused. They were gaps we found in industry involving the ability to look at the quality and quantity of data sets. Now we went back to industry and said, okay, what do you consider to be best practices for actually data set generation. Data set generation in terms of how you develop synthetic data, how you apply truth data to your labels. These are areas we will discuss in more detail in follow-on videos. The 8th AI level of rigor task is called k-fold variation. And if you ever heard of the term k-fold cross-validation, it's a variation of that. What it basically does is it separates out test and evaluation data to use from all the other data that's being used to actually train and develop the AI model. Why is that important? Well, you want an independent test done on your system. So we provide a basic mathematical approach to randomly select that data in order to ensure that you have an objective test and evaluation structure when the model is ready to be operationally tested. The 9th AI level of rigor task is called Missing and Sparse Data, Class Requirements, and Actual Results. And they're tables. And these tables were specifically built here at WD to understand or bound the problem of missing and sparse data issues. They're a way to represent what is required to be compared to what is tested. And it's another way to give you confidence in terms of how the model is handling the operational environment. We will go into details on how to put the tables together, what the tables consist of, the columns and the rows in future videos. The 10th AI level of rigor task is called confusion matrix creation. You might have heard of confusion matrices. They're an industry standard. We go into detail on how to develop a confusion matrix and why they're important in terms of how to measure in an objective way performance of an algorithm. And the importance of that is that when someone says, hey, I've just developed an algorithm, an AI algorithm, and it's so much better than traditional software, the question you want to ask them is, can I see your confusion matrix? Because it determines exactly how much better it was or if it was really better. It ensures that data is not hidden, performance data is not skewed or changed or biased. It ensures you have an objective view of the performance of that algorithm. The 11th AI level of rigor task is called ROC-AUC or PR-AUC analysis. I won't get into a lot of detail, but consider that in the previous lore task, we actually looked at performance and being able to analyze performance. In this lore task, what we're now looking at is a way to compare performance of various algorithms and how they're tweaked and how they're managed in a way to optimize them and then compare which one would be the best to represent that function. And so this is about a comparison analysis, and we use it in a way to do comparison analysis. Once you understand what the performance is, now compare performances. And again, we stay in an objective way. We want to objectively look at things. And so you want your data scientist to say, okay, have you compared this algorithm with another? Or did you just select one algorithm? You want a comparison to show why this algorithm is the best AI algorithm to meet those functional demands. The 12th AI level of rigor task involves bias, variance, and the sweet spot. All technical terms describing various aspects of algorithm performance. Consider the previous two lore tasks, one on the confusion matrix, the other one was on the ROC-AUC, PR-AUC. They provided an analysis, a comparison analysis, a performance analysis. Now what we want to do is we want to look under the hood of that algorithm that created those results. And we want to look under the hood in terms of best practices. And some of those best practices are in the form of bias, variance, and sweet spot. And we'll get into a lot more detail of all of this later and the mathematics of it all. But bias basically indicates how much did I have to bias or change the algorithm specific to that data set to make sure it had a good success rate. Variance says, well, if you biased it so much, how would that affect other data sets? Did you bias it so specifically? Did you customize it so much that other data sets will perform poorly? And then the other area, sweet spot, says, how did I modify my hyperparameters to get those wonderful results that we're looking at? We want to have this all documented, we want to have this all discussed, so when we look at those graphs, we also have the history, the background of what created those algorithms that produced those graphs. The 13th AI level of rigor task is called the subsystem hazard analysis format. Consider that the AI function, the AI model, is now a subsystem within a system, and there are other subsystems that are interacting with this subsystem. What happens when those subsystems fail? How will that affect the AI function? Was that considered? How was that considered? What will be done in order to ensure that the AI will still perform adequately if other subsystems fail? At least, is it being considered? Is it being analyzed? Is it being bound? That is the purpose of AI Level of Rigor Task 13. The 14th and final AI Level of Rigor task involves best practice discussions about AI/ML algorithm development. We talked a lot about some best practices when we talked about confusion matrices, RLC AUC, doing analysis of bias and variance. But now we're specifically involved in the development of the algorithm itself. And some things that are involved in the algorithm development might be specific to the actual algorithm. If you're using a convolutional neural net, what specifically do you need to do? If you're using some type of deep neural net, what specifically are you doing? If you're using like a random forest, what specifically supports random forest best practice development? Those are things that we're looking at discussing in our final level of rigor task. We just reviewed all 14 level of rigor tasks. And I want to reemphasize that they were all derived from actually working in a sandbox environment with the robots and the mission planner. So when would you use these tasks? Would they be used in the requirement stage, in the algorithm development stage, in the test and evaluation stage? Where would you use them? Would they be used in multiple places? And how would they be used in multiple places? Let's talk about that next. Let's get into the actual stages, describe those stages, and how the 14 lore is applied across those stages. So the first stage is requirements. And requirements, we're all familiar with exactly what is required out of the system. And AI is part of the system. So when we look at requirements, we're looking at it from a systems perspective, but particularly what does AI need to do? And we're going to review this in greater detail, but we went through 9 of those 14 lore tasks that really related to making sure that we define things in the requirements specific to the AI within the system. The next stage is architecture. You have requirements. How are you going to design this process? And I think it's really important to understand that we're looking at a system level architecture where AI is part of that system. And in the future video, we're going to go into details on, is it really that different? Is an AI function in a system different from a traditional software function? I think it's important for you to know that. And so 4 of those out of those 14 are going to apply to architecture. For stage 3, we're focusing on algorithm design. In algorithm design, we're applying 6 of those lore, and algorithm design is specific to how you design the algorithm. And if you remember, we talked about some of those things, like a confusion matrix or an ROC AUC. So we're going to get into more detail on what those are specific to an algorithm design. Stage 4, algorithm code, is applying 6 of those lore. And if you notice that there's overlaps because we have a relationship between requirements and architecture, and some of those lore overlap each other. And finally, in the stage 5, we have a test and evaluation, and we're applying 7 of those. And if you can imagine that some things that we did in requirements, we need to trace down traceability all the way through the system, finally to test and evaluation. So if you see overlap, if you see those 14 used again and again, they're used again and again in a different way specific to that stage, and that's the process of traceability. And that finally gets you to the end result, and that end result will provide you with the confidence to know that the deployed system will perform as expected. So here you see the 14 tasks in a table where each of those stages identify which of the 14 tasks will be used. The question becomes, how do those 14 level of rigor tasks apply to confidence level? And the obvious answer is that if you apply all 14 against all 5 stages, you have the most confidence, what we call highly confident, in the behavior of the deployed AI. And why is that? Because you're getting into all aspects, as we previously described, of how the algorithm fits within the system and how it's being developed, and even the nitty-gritty of the various parameters used to develop the code. I like this table because it highlights the fact that you're using all 14 lore against all 5 stages and where they apply. And I think it's important to know that if you do this, this is your highest degree of confidence. You become highly confident in the behavior of the deployed system. The next question becomes, what happens when you start to eliminate some of these stages? When you start to eliminate a stage, you're starting to eliminate control over the process. So if you want the most confidence in how an AI system is going to behave, we first state that you need to eliminate the algorithm code design. So you still have requirements, you still have architecture, you still have algorithm design, and all the lore associated with that, but we skip over the algorithm code and go right to test and evaluation. If you want a graphical depiction of what that looks like, this table, I think, very nicely shows how we're skipping over the algorithm code, but doing all the other stages. It also shows how still all 14 lore are in play. You're just skipping over some of the traceability steps between the algorithm design and algorithm code. Again, let's say we need to move back a level in terms of how much confidence we want to have. And that could be because we just don't have the money to do everything. There's a time constraint. But what we do is we now take away the algorithm design. We're getting less and less underneath what's going on with the algorithm and getting more at a higher level. And we're looking at requirements, stage 1, architecture, stage 2, and test and evaluation. A graphical depiction of what that looks like is in this table, where you notice that both the algorithm design and algorithm code are not being used. And I think it's important to understand that there are now only 10 lore tasks, 1 through 9 and 11, that are being implemented in various stages throughout the process of development. You have now decreased your ability to have confidence. We just call it a level of confidence. And it makes sense because you no longer have insights into the algorithm design or algorithm code. If you want to be just somewhat confident in how AI is deployed, we recommend that you use stage 1 requirements and stage 5 test and evaluation. You're eliminating 3 of the stages, but you're still ensuring that you have a set of requirements associated with the AI development, and you're testing those requirements during stage 5 test and evaluation. This is a depiction of how you would represent only using requirements and test and evaluation level of rigor tasks. Where they're applied, you see it's 1 through 9 and again 11. And again, this gives you somewhat confidence in the behavior of the deployed AI. If you want minimal confidence, we recommend at least going through stage 1. And there's only 4 lore tasks that we're going to recommend you go through. And I think that when we review the lore tasks again, it will make a lot of sense. But remember, the first lore tasks involve just justifying that you're using an AI system and what level of autonomy. So this is about just using the first 4 level of tasks. You'll have minimal confidence, but at least you'll have some level of confidence in the behavior of the AI when it's deployed. This is a depiction of confidence level 5, meaning minimal confidence, only using the first 4 lore in stage 1 requirements. You get to select the confidence level you need for your project. And you notice that you can go from highly confident using all 14 lore across all 5 stages, or minimally confident where you're just using the requirements stage and it's only the first 4 lore. And it's up to you. A lot of things are based upon your budget, your schedule, your manpower. But I will say this, if your system has to perform a critical function where lives could be lost or significant damage to property may occur, then I would highly recommend that you use all 14 laws. If it's doing something like giving you a recommendation of moving logistics around, maybe you don't need all 14 lore against all 5 stages. That's really up to you. But in this, we give you the ability to select whether you want something highly confident or minimally confident. At this point, it's quiz time, and I'm going to ask you some questions regarding confidence level and lore tasks, and let's see how you would respond. Confidence level 1, meaning highly confident. That means all 5 stages, all 14 lore, very rigorous. Are there any projects involving AI that you feel need this level of rigor? Could you afford it? Do you have the schedule? Do you have the manpower? These are all the things you need to think about before you even begin to work a project like this. Level 2. If you can't do level 1, can you at least do level 2? Is there a need for it? Why would you pick level 2 over level 1? What would be the issues that you'd face? Confidence level 3 means confident. That means you're only using 3 stages. You're excluding algorithm design, algorithm code. You're not looking under the hood. Your tasks are limited to 1 through 9 and 11. Why would you exclude algorithm design and algorithm code if you want to be confident in your system? Why would you make this choice? I want you to think about that. Confidence level 4 means somewhat confident. This means you're only doing requirements, test and evaluation. This is a tough situation. You don't really have a lot of insight into what's actually happening in terms of architecture, algorithm design, algorithm code. But you might be limited to this because you might be acquiring this AI from a contractor. That contractor might say that you can define requirements, you do test and evaluation, and that's it. Would this make you a little nervous? Would there something in that contract that would say, hey, I'd like to get more involved in the details and understanding what's actually going on under the hood associated with that algorithm? These are things to consider. Confidence level 5 means minimally confident. And boy, I mean minimally. All you're doing is you're setting up some requirements to justify really the use of the AI algorithm. And be really careful if you choose level 5, because truly you have the least control over the process. So here's a summary, all 5. And I want to emphasize the fact that when you start to reduce the number of lore tasks, you reduce your confidence. And it's very important that you can justify to yourself why you want to do that. And there could be great reasons, as I discussed before. But let's say you get down to level 5. Are you really confident that that system will perform the way you think it will be? And wouldn't you always want to be at level 1? I'm not saying you can, but I'm saying, wouldn't you want to? We've just went through a lot of information, and I'm sure at times it felt overwhelming. So let's ask the basic question: why the need for unique AI lores? If you remember, humans create the code that gets deployed. For computers, humans oversee how the training set is used by the algorithm to develop the model that gets deployed. And the algorithm itself will have 4 elements. It'll have the input format, it'll have the requirements, it'll have the math techniques, and it will have the output format. Here's the rub. If the computer creates poor code, if the AI model isn't developed sufficiently, with quality, with control, you may cause unwanted deaths or injury, unwanted property damage, or unwanted self-destruction. So what we did was we provided you with 14 lore tested through a sandbox, developed through that sandbox, that gives you levels of confidence. We gave you 5 levels of confidence. You get to choose how much confidence you want in the behavior of that AI system when it's deployed. You get to choose the level of confidence that best suits your needs. And I want to reinforce that if you want both those things, reliability and confidence in behavior, you need control over that process. You need control in all 5 stages and using all 14 lore. So I ask you as a final question, what is the level of confidence you would like to see in the behavior of your AI? Well, that's it, folks. That was our first video in the series. I hope you enjoyed it. I had a lot of fun describing those specific aspects of artificial intelligence, machine learning to you. I think you see where we're going. Our next video is going to focus on what makes a good or bad AI system or design or algorithm or AI in general. Some other things we're going to talk about are the system engineering aspects of artificial intelligence. You know, a lot of people talk about developing AI, but what's it look like actually within a system? So we're going to get down into also more of the nitty-gritty of the AI lore and the measurements, the structure. How can you use the AI lore, in essence, to give you control over a process of developing AI, to make you in charge, to ensure that you have the ability to be personally successful in managing an AI project? So it's an exciting series. I hope that you start to understand that this is about providing you with the ability for you to be successful in developing quality AI. And I want to thank you for listening to what I had to say, following the video. For those people that participated, I really want to give a shout out and say thank you, and look forward to seeing you at the next video. Take care.